Okay, so we're going to pick up where we left off last time. We were talking about the importance of structures in organic chemistry, and we were talking about drawing our Lewis structures. You learned how to draw Lewis structures first in Chem 1A, but we were talking about how since we're focused on so few atoms in organic chemistry, we can sort of boil down our rules into just simple number of bonds and number of lone pairs that each element likes to have. And as long as we follow these rules here, we'll draw a legit Lewis structure for any molecule. It doesn't have to just be the small ones you learn how to do in general chemistry, but even larger ones as well, okay? So I want you to see if you can draw me two constitutional isomers, two distinct structures that share the same chemical formula, C2H6O. All right, so let's just remind ourselves, how many bonds does carbon like to have? 4, and how many lone pairs? 0. So carbon wants 4 bonds and 0 lone pairs. What about hydrogen? How many bonds? Just 1. How many lone pairs on that hydrogen? 0. Hydrogen's weird. It's so teeny tiny, it can only fit 2 electrons in its valence shell. And then what about oxygen? How many bonds? 2, and how many lone pairs? Gotta have 2 to complete that octet. Okay, cool. So as long as we follow this, we'll have a legit structure. Okay, kind of the easy one, or the one that I assume everybody would get first, is just putting our carbons all in a line, and then the oxygen at the end. Right? Remember, we said always fill in the hydrogens at the end. They kind of decorate the outside of the molecule. So in this case, I need to make sure that my carbon on the end here has its 4 bonds total. So I'm going to fill that in with 3 hydrogens. Okay. The carbon in the middle already has 2 bonds, so I'm just going to put in 2 hydrogens. Okay. We said oxygen likes to have 2 bonds. That means I need 1 more hydrogen on there. And then I'm going to be good and fill in my lone pairs as well. Okay. And again, the orientation of how things are on the page doesn't matter. If you had your hydrogen, for example, pointed down and the lone pair over here, that's the exact same structure, right? What's important is who's bonded to who and where your lone pairs are, okay? So if I'm going to draw a constitutional isomer here, that means I have a different connectivity of atoms. So I can't link these up the same way, carbon, carbon, oxygen. I got to switch that up to get a new molecule, to get a new constitutional isomer. So instead, the other one that we can do is we can put that oxygen atom in the very middle. Okay? Again, I'm going to fill in, make sure my carbon has it's 4 bonds. And what else do I need to finish this structure off? The lone pairs on the oxygen. Okay, so these two molecules here, they both share that same molecular formula. All right, but they are two distinct molecules. They have very, very different chemistry, different boiling points, different melting points, different reactions, et cetera, right? They're two distinct molecules. So again, all that to say that when we're starting to do reactions in organic chemistry, you'll never see us use just the chemical formula. It's not enough information, right? We always draw out the structures. And what we're going to kind of build to is this shorthand of drawing structures so that when we do draw our structures, it doesn't take forever like it does to draw these Lewis structures, especially if you have a large molecule. Lewis structures are just a pain in the butt. They get really busy, they take a long time to draw, so we have a little bit of a shorthand that we're going to learn. Okay? Before we move on to that, though, we're going to discuss what's called formal charge. All right, so what is formal charge? Formal charge is a measure of the electron density on an atom. We can even say in a chemical structure. All right, so we're going to be able to look at a molecule and determine what the formal charge is on all the atoms in that structure. Okay, and again, that's just a measure of how many electrons there are centered on that atom. Okay, when we made our little chart up here for our rules of how many bonds and how many lone pairs, we said that this was how many bonds an element likes to have, right? We said carbon likes to have 4 bonds. What the heck do I mean by likes to have? Okay, that means that carbon is its most stable when it has 4 bonds and 0 lone pairs, and when it's its most stable, it has a formal charge of 0. Okay, so we said this is how many bonds and lone pairs an element likes to have. What we mean is how many bonds and lone pairs that element has to give it a formal charge of 0. Okay.
Do all atoms like to have a formal charge of 0?
Correct. They are always their most stable when they have a formal charge of 0 for all atoms. Okay. So we're going to say atoms like to have a formal charge of 0. That is when they're the most stable. Okay? So that's all well and good, but when chemical reactions occur, they usually don't occur between 2 super stable molecules. Okay? Oftentimes there is some unstable intermediate structure that they pass through, and that's what's driving this reaction forward. So although it's all well and good to talk about atoms when they're most stable, it's important to also spy these formal charges that an atom might have, because typically those are really the species that are involved in chemical reactions. All right? So it's not that we'll never see formal charges other than 0. In fact, those will often be what we see in chemical reactions. All right, so we're going to make a little cheat sheet table for our most important elements here. We're going to start with oxygen. Going to be very similar to the table, the cheat sheet table that we made before. Okay, we're going to have 3 columns. And now we're going to have 3 rows here. We're going to keep track of number of bonds, number of lone pairs, and lastly, formal charge. All right, and we're going to put the most stable formal charge of 0 in the very middle here. And again, if we're talking about oxygen, we said oxygen likes to have 2 bonds and 2 lone pairs. All right, so up at the top, I'm just going to draw an example. Here's my oxygen with 2 bonds and 2 lone pairs. All right. Now, we're going to take this same oxygen here, and what I'm going to do is I'm going to convert one of these bonding pair of electrons into instead a lone pair of electrons. So I'm going to erase a bond and replace it with a lone pair here. So that was a pair of electrons that oxygen was sharing with the neighboring atom, and now all of a sudden that pair of electrons is sitting just on that oxygen atom. It's increasing the electron density of that oxygen atom. So now oxygen doesn't have a formal charge of 0. It would have a formal charge of -1. Right? Remember, electrons are negatively charged. I'm increasing the electron density on that oxygen by converting that bond into a lone pair. All right? So whenever we see oxygen with only 1 bond and 3 lone pairs, right? We decrease the number of bonds and increase the number of lone pairs. We decrease its formal charge. And we got to put a minus sign on our structure. We have to indicate that formal charge on our structure. I often see it with a little circle around it as well. Sometimes that gets a little messy. Okay? Cool, so what if I do the exact opposite? What if I take my nice, stable, formal charge of 0 oxygen atom and I erase one of these lone pairs that was sitting just on that oxygen atom and convert it into a bonding pair of electrons? Is that going to increase or decrease the formal charge? It's going to increase the formal charge to +1. Right? So now I have 3 bonds and 1 lone pair. Okay. And that will give that oxygen a formal charge of +1. All right. That's all the charges, formal charges you'll see on oxygen in organic chemistry. It's not going to have a -2 charge. It is super pissed off at that point, right? It's already mad enough having this formal charge of -1. So you're never going to see it higher than that. All right. Cool. So now let's move on to our other heteroatom that we like to use a lot. That's heavily featured. That is nitrogen. I'm going to just copy my chart here and erase our values. Okay. Let's fill in this middle one together here. We say if nitrogen has a formal charge of 0, how many lone pairs does it have? I guess I did that in a weird order. How many bonds does it have? 3, and then just 1 lone pair. Okay. See if you can't fill in the rest of this chart based in analogy on what you did with oxygen, replacing bonds with lone pairs and vice versa.
Average is the charge usually just 1, like either 1 negative or...
Yeah, yeah. If you are thinking about ionic compounds, there are ions that will form higher charges, but you won't see those in organic chemistry molecules. Yeah, go for it. All right, so based an analogy of what we did before, we're going to take this bond and we're going to replace it with a lone pair. That's going to increase the electron density on that nitrogen. So when I decrease my number of bonds and increase my number of lone pairs, I get that formal charge of -1. And if I do the exact opposite, I take that lone pair and make it into a new bond, make it into a bonding pair. So I increase the number of bonds and decrease the number of lone pairs. That has the effect of giving that nitrogen a positive formal charge. Okay. Cool. All right, so we got 2 more to go here, 2 more little cheat sheets to make. One we need to do for our halogens, and then the other we need to do for the star of the show, carbon. Okay, we're just going to pick a halogen. Chlorine is a popular one that we will see often in this course. These halogens like to have 3 lone pairs and just 1 bond. That's when they have a formal charge of 0. Okay, so take a second and fill in our chart for a formal charge of -1 and +1 based on what we've been doing. Okay. And just because there's no periodic table in this room, we're not really in a science room, I printed out periodic tables just so you can kind of stick it in your notebook. We won't really need to reference it quite as heavily as you do in like a general chemistry course, but it is a chemistry course, so we should have a periodic table here. Let me show you one more, sorry. Yeah.
So, for example, chlorine, when it has 3 lone pairs and 1 bond, is that its like most natural state?
That's its most stable state, aka when it has a formal charge of 0. Yeah, so all these bonding patterns that we discussed at the beginning when we said it likes to have, what we were really saying was that's when it has a formal charge of 0. Okay?
Does it naturally occur? It can naturally occur in various states.
It can, but the most stable form in terms of a free energy standpoint, right? If you're calculating the energy of that atom, its most stable form is when it has. So that's not to say that it never appears in a slightly higher energy state, but it's just saying what the most stable state is. All right, if we decrease number of bonds and increase our number of lone pairs, that means we have 4 lone pairs and that formal charge of -1. Okay. And if we do the opposite, we increase the number of bonds and decrease the number of lone pairs. That has the effect of increasing our formal charge to +1. Okay. Now, about this chloride ion, these halide ions when they have a -1 charge, we can make note that our halogens are the elements that are most stable with a -1 formal charge. So you do very often out in nature see these halogens in this formal charge state of -1. Sodium chloride, for example, table salt, is an example of a chlorine as a chloride ion, right? The halogens just being very electronegative. It's also got a weird thing to do with size. I'm not going to go too far into it. But just to note that our halogens are going to be, out of all the elements, they're kind of okay with having that formal charge of -1. They're not quite as mad as all the other elements would be. All right, and so lastly, we got to do carbon, because of course this is an organic chemistry course. Carbon likes to have 4 bonds and 0 lone pairs, meaning it has a formal charge of 0. Okay. Everybody take a second and fill in the formal charge of -1 column. We're going to do the positive column together here. This one's a little weird. No, it's yeah, exactly. You can't increase number of bonds, right? Yeah, I'll show you here in a second. Okay, so for formal charge of -1, the same rules we've been playing. Decrease bonds, increase lone pairs. So that's carbon that has this lone pair and only 3 bonds, giving it a -1 formal charge. Because it's carbon, we have a special name for these here. Remember, positively charged ions are called cations, and negatively charged ions are called anions. So when it's carbon, this would be what's called a carb anion. All right, so we just give it a special name here when we're talking about carbon. All right, so if I was going to follow my normal patterns that we were doing before, we would increase the number of bonds and decrease lone pairs. Well, I got no lone pairs to decrease, right? Not only that, but if I tried to give carbon 5 bonds, everybody's like organic chemistry brain needs to collectively explode right now, all right? Carbon will never have 5 bonds, will never exceed its octet, okay? So these positively charged carbons here are kind of weird. They only have 3 bonds and 0 lone pairs. You have to remove that pair of electrons. Yep. Okay. So now we have 3 bonds and no lone pairs, giving it a positive charge. Again, because it's carbon, we got a special name for this. This is a carbocation. And carbocations are very common intermediates in chemical reactions. They're not very stable, so they don't exist for very long, but they're often a midpoint in the middle of a chemical reaction in organic chemistry. Okay? And what we want to note about this carbocation that is different from literally every other thing that we've made a chart on here. Oxygen regardless of formal charge, nitrogen regardless of formal charge. Our carbocation is the only time that we're allowed to break our octet rule. All right? Oxygen will never break its octet rule. Nitrogen never break its octet rule. The halogens never break its octet rule. Carbon's a little bit of a weird one in that when it forms these carbocation intermediates, it does indeed break its octet rule. Okay? So let's just make note. Our carbocation here, this has an incomplete octet. All right, and maybe we just want to say all other elements will never break their octet. All right, if you're drawing an oxygen that only has 6 electrons, something went wrong somewhere. Okay, cool. So what I'm going to do is I'm going to put down a structure of a molecule, and you're going to fill in any missing lone pairs and formal charges that should be there. So those heteroatoms are missing their lone pairs and their formal charges. Oh, my bad. Y'all don't know what the hell you're looking at. I just jumped ahead to these bond line structures. My bad. Okay. Like, what the heck is that squiggly line? Fun fact, we will learn here in just a minute, but yes, we do not know yet. My bad. There we go. Okay, that guy. Fill in lone pairs and formal charges. If I draw this oxygen with 3 bonds, how many lone pairs am I going to have to fill in? Just one, right? Gotta have that complete octet. And an oxygen with 3 bonds and 1 lone pair will have a formal charge of +1. So we can just put that positive sign there. Okay? My carbons have 4 bonds. Please note this carbon right here does indeed have 4 bonds. 1, 2, 3, 4. It's just a double bond. If I get to my nitrogen, this only has 2 bonds. So how many lone pairs do I need to fill in? 2. And then the formal charge on that nitrogen with 2 bonds and 2 lone pairs? -1. Cool. Okay. All right, so what I tried to jump into here was one of our more advanced representations for chemical structures. The first one that we're going to cover are what are called condensed structures. Okay. This is how we can represent the chemical structure of an organic molecule unambiguously, but all just written in one line, okay? These are especially popular in things like computer databases and textbooks because computers don't let you draw Lewis structures very easily, right? So if you need to write something all in one line, you would use one of these condensed structures. For our purposes, I'm not really too concerned with you being able to draw them as much as being able to interpret them, being able to read them, okay? So again, this is a structural formula. written all in one line. And we need to be able to read it. Not really concerned with you writing them. All right, we're going to be drawing structures. Okay, so we talked about a Lewis structure. So let's put down a Lewis structure for a molecule with 3 carbons. Okay. If I'm going to do my condensed structure, you're going to list each carbon atom followed by what it's bound to. All right, so this first carbon atom is bound to 3 hydrogens, so CH3, and then you're just going to move on down the line in your structure. So my next carbon atom, what will I put? How many hydrogens? 2, CH2. The next carbon, 3. So that would be the condensed structure of that same molecule. All right, just written out all in one line. Okay, cool. So then, again, I'm more concerned with you being able to read these here. So let's put one down, and you're going to draw me the Lewis structure. Okay, so we now have 5 carbons all in a row, just a straight chain here. So now I got to decorate each one with their hydrogens. Okay. An equivalent way of writing this condensed structure that's even more condensed, because in the middle of this molecule we have a bunch of repeating units, CH2, CH2, CH2. So another way that you would see this same exact molecule is CH3 in parentheses CH2 with then the number 3 outside, telling you that's how many repeating units you have. Okay, so when we have our parentheses with that subscript, that means we have these repeating units. And so you can see that if you're doing this like 10 carbon molecule, using your condensed structure can save you quite a bit of time compared to drawing out your Lewis structure. All right. The other thing that you will see is something like this. Okay. So now we have these parentheses without a subscript. This is how you indicate a branch point, or indicate that something is sticking off of the main chain. So this indicates a group is pointing off that main chain. So in this case here, I have my first 3 carbons that are linked together. My CH3, my CH2. But when we get to that 3rd carbon, it's just CH. So what's that other bond? Because carbon's got to have 4 bonds. That's that methyl group that's in parentheses there. That's that CH3 that's in parentheses. It means that that is sticking off of that main chain. Okay, so again, let me just color code here. In parentheses, this CH3 corresponds to this CH3 that's sticking out of the middle here, off of the main chain of that molecule. Okay, so then the last thing that we want to note about our condensed structures when we're drawing them is we need to follow our rules for our octet. So follow our octet rules. Okay? So let's just do a few more. so for this first one, we have our 3 carbons. And in parentheses, that OH group indicates that it is sticking off of that main chain. Okay. This next one here, we have this CH3 in parentheses with the 2 outside, right? So we got that sort of repeating CH3. Okay. But the problem that I sort of imagine maybe people got themselves into is if they try to connect these all together here, CH3, CH3, you're done. You plugged up all the sort of bonds on that molecule. So where the heck is the rest of this here? The back half of that name, okay? So indeed there are 2 of those CH3 groups, but they can't be linked together, otherwise that sort of violates our formula here. They're both going to be located on this carbon here, right? Because otherwise that carbon doesn't have its complete octet. Okay, so I have my carbon with its hydrogen, and it's got these 2 CH3 groups on it. I'm going to color code here just so we can keep track of who's who. Okay, this carbon is going to be the one with those 2 methyl groups. Okay. I sort of wanted to make a point by putting one pointed up and one pointed down. If you, for example, had swapped out this CH3 and this hydrogen, that's perfectly fine as well. That's the same structure. Okay, just sort of drawn differently on the page. And then I'm just going to continue the rest, my CH2 and my CH3. All right, so that was a little bit of a tricky one. Again, just make sure that you're not breaking your octet rules, right? That's kind of the only way that you can draw that molecule such that everybody's all happy and satisfied and has their octet rule satisfied. Same thing down here. This one is a little tricky as well. We're going to say, all right, CH3. We got another C with an H and an O. What's the problem with this structure here? The oxygen's not happy, the carbon's not happy, right? We're violating some octet rules here. Okay, well then can I just go in and stick a bunch of hydrogens? No, because then it's not that same molecular formula, right? Now I'm changing my formula by adding extra hydrogen. So I can't do that. How do I make my oxygen and my carbon happy? What am I going to use? Double bond. And of course, be good with my lone pairs here. You'll sort of see certain patterns over and over again. This CHO always indicates a carbon with a double bond on the end of a molecule here. Okay, so we kind of see certain patterns over and over again. Now you can think of some crazy molecules and be like, oh man, how the heck do I write the condensed formula for that? If it's too complicated, we don't try to do the condensed formula. The condensed formula is really something you'll see for fairly simple molecules. When stuff gets too complicated, it's like not worth it. It's making your life more difficult than it needs to be. What's up?
So when they're in the parentheses, like in the top right, they don't have to be like neighbors, they just have to be both.
It really depends on the context. If you can, so CH2s, you'd link together, right? CH3s, you just can't. There's no way to do it such that your molecule actually makes sense, right? So again, kind of the default rule that you always have to fall back on is that octet rule, making sure you're drawing a structure with complete octets. There's a little bit of trial and error that's going to be at the beginning, for sure, all right? But yes, okay. And now, very excited to finally introduce, because it's just by far the easiest way to draw, what are called bond line structures. All right, after this first chapter, after we sort of establish our rules and our octet rules and everything like that, we're going to pretty much abandon Lewis structures altogether because they're a pain in the butt to draw. And so pretty much exclusively after this first week, we're going to start defaulting to these what are called bond line structures here. All right, so let's just put down an example of a bond line structure. That is these zigzaggy lines that you see associated with organic chemistry. All right? The famous hexagon is another example. Okay, so these represent chemical structures. So the first thing we got to do is we got to learn how to read these structures here. All right? What makes these structures very awesome and easy to draw, but also a little bit more complicated, is that the position of carbons and hydrogens is implied by these little line segments here. Okay? So, for our bond line structures, we have carbon atoms at every endpoint and intersection. All right, so in my example molecule here, first thing we're going to learn how to do is just sort of read these structures, count how many carbons there are. Again, there are carbons at every endpoint of my line segments and every intersection where two of those line segments meet. All right, so this little zigzaggy line here would depict a 5-carbon compound, right? Again, endpoints and intersections. 1, 2, 3, 4, 5. All right, the hydrogens are also implied. So how do I know how many hydrogens to add? Hydrogens, we're going to fill them in to give every carbon a full octet. All right, so our goal here when we're going to start out, we're going to be looking for these molecular formulas. I'm going to put down bond line structures. You're going to give me a molecular formula like C whatever, H whatever. We got to figure out how many carbons and hydrogens there are. Right? Again, we counted carbons at every endpoint and intersection. So my formula is C5. All right, now we got to figure out how many hydrogens we have. And what we're going to do is we're just going to go carbon by carbon, and we're going to fill them in to make sure that our carbon atoms are happy, that they all have their 4 bonds. Okay? So this very first one on the end here, how many carbon-carbon bonds do we have drawn? Just one. So then how many hydrogens are there going to be decorating the outside here? 3. I need to make sure that each of these carbon atoms has those 4 bonds that they like. Okay? Going down the line, now what about the ones in the middle of the molecule? How many hydrogens am I going to have to fill in for each of those? 2. Right, and then lastly, the other one on the end there will also require 3. So that brings me to a total of 12 hydrogens in this molecule. Okay, so our carbon atoms are implied. They're at every endpoint and intersection. And the hydrogens you just fill in to make sure that your carbon atoms are all happy. All right? Our goal is to be really good at this so that when we look at a structure, you'll see me tapping away all the time to count carbons. All right? And then we got to kind of like just fill in with our mind's eye where those hydrogens are located. Okay? What's up?
last lecture you said that every structure has to have a carbon and a hydrogen.
So if it's an organic molecule, then yes, every organic molecule by definition has carbons and
So
hydrogen.
that makes it much more easy to assume.
Oh, and that's why those are the two elements that are implied in those structures, because every organic molecule we're going to be drawing has carbons and hydrogens in there, right? And that leads me to the last point of our bond line structures. Every other atom in organic chemistry, what we call heteroatoms, those are going to have to be explicitly drawn in there in your structure. So if you had any nitrogens or any oxygens, you would see an O or an N in your formula, or in your structure rather, okay? So all heteroatoms and their hydrogens are explicitly drawn. Okay, so let's, for example, take this Lewis structure. All right, we did its condensed structural formula. We have its Lewis structure. Let's turn this thing into a bond line structure here. All right, so how many carbons am I going to draw? 3. And so 1, 2, 3 carbons. Okay, we can sort of color carbon on the end, blue, carbon in the middle, red, carbon on the other end, orange, right? Those are my 3 carbons in that molecule. The hydrogens on those carbons are all implied, so I don't have to do anything to draw those hydrogens. But this OH group here, I do have to draw. And so what you would do is just put an OH on that red carbon. So all heteroatoms and any hydrogens that may be bound to that heteroatom. So not just O with the hydrogen implied, you have to draw that hydrogen in there on that oxygen.
So you're gonna have to put the little bond symbol right there in between the O and the H.
Yeah, you do draw a stick to show that that oxygen is connected to that carbon.
The hydrogen.
Oh, that you could do either. You will honestly often see it more compactly written, but then if there's a reaction that involves that OH bond, they might draw it in there, like, basically put a stick between there is what you're saying?
Mm-hmm.
Either one of those are perfectly fine. Depending on the context of how you're using that functional group, you'd see it both ways. All right, cool. So let's start with the reading, and then we'll graduate to the drawing here. All right, I'm going to put down a bunch of bond line structures. You're going to give me the chemical formula, the molecular formula of those structures that we drew. All right, so again, step 1, we're going to read them. Right, and just for the sake of me being a pain in the ass, I also want you to fill in any missing lone pairs. Okay, and to be clear, just the molecular formula, so C what, H what. In this case, there's going to be some N's in there as well. So remember, it's the same as if I had drawn that bond there. So hydrogens, we kind of get lazy. We just kind of put them right next to it. What's up?
I don't know what that extra line about that.
So that's a double bond now,
Oh.
a carbon-carbon double bond. Oh yeah, good question. All right, so that's going to influence how you count the number of hydrogens that should be about those carbons as well. All right, so first of all, I said fill in missing lone pairs. Where do I need to put lone pairs in these three examples? Metal structure. Okay, the reason why I'm going to sort of hammer this home is as you sort of go on in your organic chemistry, your chemistry career in general, they stop drawing in the dots all the time, right? Because once you're sort of well trained, you know where they should be. So your textbook's going to be really good at always drawing them in there. You do some random Google and start reading about this stuff, you might see some structures that don't have lone pairs on there. And again, that's because they're implied, because we know nitrogen always has to have its complete octet. So if it's got its 3 bonds, it always has 1 lone pair, right? We just know that to be true. Okay, I am going to count carbons here. So again, all of my endpoints and intersections, 1, 2, 3, 4, 5. Okay, if we go in and we fill in hydrogens, we have all these ones at these endpoints here. They're all going to need how many hydrogens? 3. So that brings us up to 9. All right, what about this one right here? How many hydrogens? 2. And what about this guy? Just 1, right? It's already got 3 bonds explicitly written, so that means my 4th bond is that missing hydrogen. Okay, so that'd be C5H12. How many carbons do we see in this structure right here? 3. So my endpoints and my one intersection here, those are my 3 carbons. I obviously just have the 1 nitrogen. If it's a 1 in your chemical formula, you usually don't draw that in there. You just leave a subscript off. Okay? And then lastly, filling in my hydrogens here. Again, we got these on the end. 1, 2, 3, 4, 5, 6. How many on this middle one? 7, 8. So I got any more? Yeah, the one that's explicitly drawn here. Don't forget to count that one as well. So that will bring me up to a total of 9 hydrogens and my 1 nitrogen.
Can you draw the condensed?
I'm gonna do that for each of these just so we have sort of an example down as well. Again, I'm not too concerned with you being able to draw them, but again, sort of learning by analogy helps. So I will put them down just so we can sort of see. But let's finish off this task. Okay. All right. How many carbons do we have in this molecule? 6. 1, 2, 3, 4, 5, 6. All right. What about hydrogens? How many hydrogens did we get?
12.
Cool. All right. So there's 12 of them. Let's make sure that we can see where those 12 are. Okay. So starting off normal, we just have single bonds. So I got to fill in 4 bonds, so 3 hydrogens. Here's the same as well. But now we get to this carbon right here, and this carbon is about this double bond. So how many bonds do I already have explicitly drawn for that carbon? 3. So then I only need 1 hydrogen to complete its octet. All right, it's already got 3 bonds drawn in with that double bond. Same thing on the other side. We'll just need 1 additional hydrogen. And then filling in the rest of them are kind of normal single bonded carbons. I need 2 on this one and 3 on that last one. Okay, so that brings me up to a total of 12. All right. So again, remember our double bond represented by the 2 sticks here means that there's an extra pair of electrons that are being shared. So in terms of my line segments that are drawn, I have 1, 2, 3 pairs of electrons. I just need that 1 hydrogen to bring me up to a total of 4. Okay, and so then just to sort of go back and look at our condensed structures for these. Okay. How you write these is you would go down the line starting with your first carbon, CH3, CH2, CH. Now we have a methyl group sticking off of our main chain, CH3. You could continue your main chain. That next one, another even more condensed way to write it would be to be using those subscripts. Either one of these would be acceptable for a condensed structural formula of that molecule. Okay. For this one here, we're again going to do the same thing, CH3, CH2. But now are we going to use parentheses for that nitrogen? No, because it is in line of the main chain, right? It's not sticking off. It's just NHCH3. It is in line of the main chain here, not sticking off. Okay. For these double bonded compounds, if it's being a pain in the butt, it might have it be just kind of implied by the number of hydrogens that are there. But typically what you would see is some sort of a hint that there's a double bond in between those 2 carbons. They would put like an equal sign or something like that to show you that there's a double bond located there. Okay, You could kind of do it this way, and there's really no other way to draw that structure where you have a complete octet rule. But what you'll see for double bonded compounds is that they kind of give you a little hint. They put a little double bond in there or a little equal sign in there.
Yeah, put the CH in parentheses.
No, because those carbons are not off the main chain. They're all on a line. Carbon bound to carbon, bound to carbon, bound to carbon.
No, like CH parentheses 2 to show that it.
You could.
Twice.
You mean condense these into just one?
Yeah.
Yeah, but typically you would see it like this, honestly, with the double bond in between those two, so you can see. Cool. All right. So then now we're going to go the other way. I want you to go from this Lewis structure that I'm going to draw. You're going to draw me the proper bond line structure. Again, I'm going to leave off lone pairs. You got to draw those in. Oh, my bad. I see what you're saying. All right, we'll start next time with these, the second one and the third one. We're going to run out of time here. So let's just do this one, okay? I want everybody to take a second and count carbons on their structure right now. You should have a total of how many if you did your structure correctly. 5. Count carbons is like the best way to double check your work in this class. When we start doing you're going to hear me say it over and over and over again. Count your carbons, right? Just a very easy mistake to make. Okay, I should have 4 of them all in a line here. Okay, so I'm going to start my zigzaggy line here. All right, there's my 4. Okay, and to be clear, if you started with like a zag instead of a zig, I don't know how to say this, but if you started with one going down or one going up, that's equivalent. That's perfectly fine. Okay, so now I need to include this carbon right here that is sticking off of my main chain, particularly off of that second carbon in the line here. Okay, now what I have a feeling a lot of people did because of the orientation in my Lewis structure is to draw that bond pointing down like this. All right, you don't want to you want to space out your lines as much as possible. This is a very misleading representation of what that molecule actually looks like. Bonds like to be as far apart as possible, right? So they're not going to all be crammed into this one little area here. So we don't want to draw it like this. Instead, you're going to draw it pointing the other direction. You're just going to draw it pointing up. So we're going to say this one's bad because we're going to spread out all of our bonds as much as we can. And so just to keep my coloring consistent, we said that these 4 were the straight chain. This is now the one pointing off of that main chain. And what else do I need to include to finish this off? That OH group. So again, OH, and I'm going to put in my lone pairs. Okay, you'll see that just kind of by default in these zigzaggy structures, the bond and the angles that we try to keep here are 120 degrees, right? Space things out as kind of like a Mercedes symbol or whatever, right? 120 degrees apart is kind of your default. When your structure gets really busy, you might have to start breaking that rule a little bit, but that's kind of how we default, okay? And it's not like it's wrong, but it's kind of like if I asked you how many brothers you had and you said 4 halves, like, okay, fine, that's technically 2, but what a weird freaking way to say that, right? It's kind of the same thing. You're just doing stuff outside the norm of how we do it in chemistry, okay? Cool, what's up? Yes, that's perfectly fine, yeah. And you will see it more condensed like this quite often. If that bond was involved in chemistry, we would draw it out. But if we don't have to, we keep things kind of condensed.